there is a very specific reason why when you say even-powered function and accidentally say it as even function, most teachers tend to let it slide a bit. Because, well, all even-powered functions are even functions. They have this characteristic. F of negative x is equal to f of x. Why is this? Well, hey, what's this? This is equal to x squared to the nth power. So with negative x, we get x squared to the nth power. With positive x, we get x squared to the nth power. Because negative x, in brackets, squared is equal to, the negatives cancel out, so we get x squared. Please note that here n can be 0. So n is greater than or equal to 0, and n is an integer. There is debate over whether or not 0 counts as a natural number, because hey, there are naturally 0 alligators here. Well, okay. Anyhow, if the exponent of every single term is even, what happens is that, hey, we're adding together numbers, or functions rather, where function of negative x equals function of x. So here we have one value, here we have the same value on either side of the y-axis. And then we add a number of exactly the same thing. So what we have is basically, hey guys, let's add x, y, z, or a, b, c over here, and let's add a, b, c over here. Do they come out to the same solution? Well, yes. So let's identify the even function and symmetry. Now use your graphing calculator if you have one. If you don't, well, you can just eyeball it. So x to the fourth. This is an even function. And this here is definitely not an even function. We can tell just by the graph. Now we can also tell by the fact that it will have coefficients that are not 0 for, say, the x to the third term or the x term. So the symmetry for the even function is symmetry x equals 0. And over here, no symmetry. Okay, so what else can we think of? Well, actually, it is possible for something that's not even to actually still have symmetry. How? Well, say we have x plus 1 to the fourth power. That will be symmetrical across x equals negative 1, because it's a transformation. Because all the numbers that used to be 1 down now look like they're, well, where they were on, say, x to the fourth. Okay, so odd functions. Well, odd functions only occur if the exponent of each term is odd. All odd functions have this mathematical characteristic. Why? Well, it's x to the 2n plus 1. That means x to the 2n, okay, positive. But the plus 1 part, hey, if x is negative, this is going to end up being negative. If x is positive, this is positive. So what we have is rotational symmetry about the origin. We also call this point symmetry. Why? Well, think about plotting a point here. And this should correspond to a point over here, more or less. As in more or less in the form of, hey, this is a sketch diagram, not a to-scale diagram. In actuality, if this here is x, and this here is negative x, then the values will be, well, one is negative the other. Which one is which doesn't matter. Because f of negative x equals negative f of x, never specified if the x is positive or negative. So here, let's identify the odd function and its symmetry. Use your graphing calculator. Well, x to the third, we have no constant term, so that's clearly this one. So it passes through 0, 0. This one, plus 1 times -1 times -2 is plus 2. So that's this graph here. So this is odd. Point symmetry. Symmetry 0, 0. And B is, well, I should point out that it is possible to still actually have point symmetry across some point. I mean, you'd have to be like, say, oh, x plus 1 to the third power plus 2. That would be symmetric across -1, 2. Why? Well, we'll get to that next section. So, here we have a not odd function. It's not even either. And no symmetry. We can't specify that it's no symmetry straight out because we don't know enough to say that yet. But we can say that there's no symmetry across 0, 0. When we get to talking about transformations, we can say, oh, there's no symmetry period. Or, oh, there's point symmetry across a point that's not the origin. All right, example 3. State the degree and sign of the leading coefficient, determine the x-intercepts, determine the end behavior of the graph of the function. Now please note the degree and the sign of the coefficient are separate things because the coefficients don't have degrees. So use your graphing calculator to check if you need to. We're not going to bother. Leading coefficient, what's that? Hey, x squared, we're going to end up with x squared. And times x, okay, x to the third. And times x again, oh, x to the fourth. So x to the fourth is degree 4. Leading coefficient is plus 1. Now, what about the x-intercepts? Well, we have 1. Well, technically we have 1 twice. We have -1 and we have -3. At these points, f of x is equal to 0. X-intercepts -3, -1, and 1 twice. What does doing 1 twice actually mean? It means that this is a tangent point. It's not, oh, we cross over and then we cross back. In the case of leading coefficient plus 1, it's cross over downward and then cross back upward. No, we do the crossing over down and cross over up at the same point. So that means this is tangent. We could label this as such if we so wished. Describe the end behavior of the graph of the function. Well, that's just leading coefficient. End behavior here plus infinity either way. So that's it for that example. Now what do we need to sketch the graph of this? Well, okay, end behavior is good. Why? We don't want to accidentally draw this as both going to positive infinity when in fact it doesn't, because x to the third times x is x to the fourth. And then negative, oh, negative x to the fourth. That means we're going down on both sides. So what else do we need? Well, we should get Y-intercepts. So these are very important points. Now, alternatively, we could use other things. For example, describe what you need, graphing calculator. Yeah, okay. I don't think the teachers are asking for that. Nor are they asking for, pencil and paper and a huge table to work out points on. What we usually want is X and Y intercepts, end behavior, which basically depends on the sign of the leading coefficient. And, well, honestly, that's just about it. I mean, you could plot a few extra points, and that's nice to plot the graph with. So let's say that. A few other points. To not look too off. So this is literally a matter of possibly being off the charts. I do realize that is such a horror bad pun that your computer screen or TV monitor may be at risk of excessive groaning. Yes, okay, example 5. Without graphing, determine if each has line symmetry about the y-axis, point symmetry about the origin, or neither. Now here we have all of the exponents even. All even exponents. Line symmetry about y-axis, or x equals 0 if we prefer. Here, well, we have mixed, odd, and even. Even exponents. So this, no line symmetry. If we add something that has, well, point symmetry across the origin, or any other point for that matter, with something that has line symmetry, that comes out to something that has no symmetry whatsoever, because the numbers you're stacking up on either side aren't going to be the same. So they aren't going to match up nicely like you do with two things that have line symmetry about the same line. And what other characteristics are there? Well, with point symmetry, if you have the same point, at least you'll end up corresponding even if the sign flips. Which, of course, means that adding this together makes something completely different. Now here I'm claiming that there's no line or point symmetry. Why can I make this claim when earlier I had to say, there's no point symmetry about a particular point? Well, I'm going to make this claim because of a reason that we're going to learn very shortly in the next section. Namely that, hey, if we want this to actually have point symmetry about a point, i.e. be a transformation, what we need is to have every exponent represented, because that has to factor together to be one, expression taken to some exponent, n, as in the leading exponent here. So that's it for this section, and we'll get to transformations momentarily.